All right. Good morning, everybody, and thank you for showing up and watching the inauguration at the same time. This is going to be a pretty soft talk, very introductory and survey-like. So I'm going to talk about the P equals W conjecture in mirror symmetry and homological mirror symmetry in particular. But it's really a part of a two-talk sequence. So the afternoon talk by Andrew, it's going to be the talk that will have actual serious new information and results. So I encourage you to go there and listen to Andrew. So anything that's new in this talk, and it's going to be very little that I'm going to say, it's going to be part of this joint work project that we're working on with Andrew, Harder and Katzarkov. And there will be some results that I want to advertise by Sukjoo Lee, who is graduating this year, which are relevant to this story. Everything else will be stuff that people already know. Since this is an introductory sequence and talking about applications, it's going to be like normal to review things. Okay, so I'll start by reviewing the classical P equals W conjecture in non-abelian Hodge theory, which actually motivates the P equals W conjecture in mirror symmetry. And I'll talk about some, I mean, it's a big subject these days. It's been around for 8 years now, and there are many interesting new results that people keep proving all the time. So I'll mention some of those. And they undoubtedly all have deep connections to mirror symmetry that need to be explored. And very little is done in that direction. So after that, I'll talk about the mirror P equals W conjecture and its relationship to homological mirror symmetry for Fanos. And so the interesting new stuff that's part of our project is kind of a refinement of the mirror P equals W conjecture, which uses SYZ mirror symmetry. And I'll mention it without details, and Andrew actually will talk about it in more details and about strategies for proofs. And at the end, I'm going to talk about some recent work of Sukjoo Lee, who is a student that Rondonagi and I are supervising, who finishes this year, who found some very interesting applications of gluing in relative mirror symmetry, first to the mirror P equals W conjecture, and then to the Hodge and deformation theory of hybrid Landau-Ginzburg models. So it's going to be related a little bit to the general story that I want to present. Okay, so let me start. Let me talk about the P equals W conjecture in non-abelian Hodge theory. So what's that about? The input for this story is what you normally have in a basic non-abelian Hodge theory as input, which is a smooth compact curve C and a complex reductive group G. And so this data gives you two interesting Calabi-Yau spaces. Well, gives you more than two, but there are two that are relevant to this story. There is the moduli of locally constant principal G bundles on C, moduli of G local systems, which I'm going to call MB, Betty. And then there is the moduli of semi-stable G Higgs bundles. So these are pairs, principal algebraic G bundles E, and an adjoint field with coefficients in one forms. So there are these two moduli spaces, which are of dimension, the dimension of the group times G minus one, the genus minus one, 2 times that. And they're both algebraic symplectic, in fact, Calabi-Yau. And there is a classical statement in its in its strongest form due to Simpson, which says that these two spaces are actually homeomorphic, which is really a combination of the non-abelian Hodge theorem and the Riemann-Hilbert correspondence. But there is some natural canonical homeomorphism between those two spaces. And in fact, if you think about them as stratified manifolds, it's really a diffeomorphism. So the interesting thing is that they're not isomorphic as algebraic varieties or even as analytic spaces. In particular, as an algebraic variety, the Betti space, the space of locally constant principal G bundles, is an affine variety over the complex numbers. Whereas the Dolbeau space, it has a lot of compact subvarieties. In fact, it has compact subvarieties through every point. But because the spaces are homomorphic, their cohomology rings are isomorphic naturally. And that, because the homomorphism is not analytic or algebraic in any way, it's unreasonable to expect that this isomorphism will preserve any type of Hodge information, and it doesn't. It does not respect the Hodge filtration on those cohomology spaces. It does not respect the weight filtrations. But this amazing Pico's W conjecture of De Cataldo, Hausel, and Migliorini, it says that this homomorphism actually converts the weight filtration on the character variety on the space of local systems to a filtration of a different geometric origin on the cohomology of the Dolbeau space. So let me just say what that filtration is. It's what's called the perverse Leray filtration. So what's a perverse filtration? I'm going to do the most basic version. So say that we have a B, which is a smooth complex algebraic variety. Then if you look at the category of constructible sheaves of rational vector spaces on B with compact support, so in that derived category, there is a natural T structure, the middle perversity T structure, which says that we're looking at complexes of constructible sheaves whose cohomologies have support. The degree I cohomology has support of dimension less than or equal to -phi, and the degree I cohomology of the Verdier duo of the complex of constructible sheaves also has support in dimension less than or equal to -i. So that's the middle perversity T structure. And the heart of that T structure is an abelian category of perverse sheaves on B. But in particular, the T structure gives you a truncation factor on the complexes of constructible sheaves, which I'm calling the perverse truncation, tau less than or equal to k for every integer k. And then you have a filtration associated with truncating at various levels successively on any complex, and then you have an induced filtration from the hypercohomology spectral sequence on the cohomology of any complex. And so the perverse filtration on the cohomology of a complex, constructible complex F, is just the filtration that has steps the image of the cohomology of the intelligently truncated complex with respect to the middle perversity perverse structure for OK. And now if you have a map from some smooth variety M to B, and the map has compact fibers, I'm calling it H, then you can define what's called the perverse Leray filtration on the cohomology with rational coefficients of M. So it's labeled, it's slightly shifted, it's labeled so that the steps are contained in the interval 0, 2 times the dimension of M minus C. C is some defect number, which I'll explain in a moment. And so this perverse Leray filtration on the ith cohomology of M with coefficients in Q has step pk, which is really the perverse filtration. So you take the push forward of Q. So the full direct image of Q, it's a constructible sheaf downstairs. You truncate with respect to the perverse T structure at level K, shift by C, and then look at the cohomology of that complex in degree I minus C that maps naturally to the cohomology through the Lie spectral sequence, maps naturally to the cohomology of M with coefficients in Q in degree I, and that's the kth step. And this guy C here, it's a defect number, so it's the difference between twice the dimension of M and the dimension of the fiber product of M over P. So that's called the semi-smallness defect. In our
Tony, isn't it
yes,
equal to the dimension of B?
so yeah, it depends. I mean, M could be a birational map, so that guy is relevant when the map H is not flat.
Okay.
When the map H is flat, I mean, it's just the dimension of the fiber.
Of the base, I think.
Sasha, I can't hear you.
I think it's the dimension of the base if the map is flat.
If the map is flat, it's the dimension of the base. Sorry, yeah, it's the dimension of the base where everything takes place. Yeah. Okay, but so yeah, I mean, in our case, it's just going to be it's just going to be the dimension of the base, because our map is going to be flat. Okay. So the point is that this Daubon moduli space of Higgs bundles, it actually comes with an intrinsically defined map, which is its affinization. So if you just take the global functions on the Daubon moduli space, and that's some algebra, take the spectrum of that algebra, let's go with B. Now you have a morphism, proper morphism from the Daubon moduli space to B. B in this case happens to be actually a vector space, so that global algebra of functions is a polynomial ring, and the map is actually the famous Hitchin map, which can be described explicitly by taking a basis in the ring of invariant polynomials for the structure group and evaluating it on the Higgs field. But it's something intrinsic. It actually doesn't depend on any choices. It's something that depends only on the variety and Daubon. And happens to be flat. In this case, in fact, happens to be an integrable system. The fiber and the base have the same dimension. The fibers are Lagrangian for the homomorphic symplectic structure. So here is the classical Pico's W conjecture of the Cataldo, Hausel, and Migliorini. It says that the homomorphism that comes from non-abelian Hodge theory between the Betti and the Daubon spaces, it identifies the weight filtration on the affine variety, which is the Betti space, with the perverse Leray filtration on the cohomology of the Daubon space. It says that the 2kth step of the weight filtration actually becomes equal to the kth step of the perverse Leray filtration. So there is a doubling here happening. It's just that this character variety, it's a very special guy. It's one of these circle compact hyperkähler manifolds. So it has this very special property that the steps of the weight filtration actually repeat in even and odd degrees. There is no difference between the even and the odd. They jump only by 2. And so these steps actually identified with the perverse Leray filtration. So that's the conjecture. And it has actually by now very rich history with very interesting results that people keep generating and expanding. So I've mentioned some of them. So the first result is, of course, the original theorem of the Cataldo, Hausel, and Migliorini, who proved that the Pico's W conjecture is true for any curve of genus bigger than 0 and any group of type A1. So SL2, PL2, PSL2, and GL2. Another interesting result, more recent, is due to Juliang Shen and Zili Zhang 2 years ago. And it says that it works actually for an orbifold curve. In fact, there is a sequence of 5 orbifold curves and groups of arbitrary high rank, but the rank depends on the orbifold structure. So if you have an elliptic curve and you take a finite group, which is going to be, well, basically the allowable finite group of group automorphisms of an elliptic curve. So it's going to be the trivial Z mod 2, Z mod 3, Z mod 4, or Z mod 6. So, if you have trivial or Z mod 2, the elliptic curve can be arbitrary. Z mod 2 is just going to be the -1 involution. But for Z mod 4, you need the square elliptic curve with complex multiplication by Gaussian integers. And for Z mod 3 and Z mod 6, you need the hexagonal elliptic curve with complex multiplication by roots of unity of order 3. And so there is this static curve that you can define, which is the quotient of the elliptic curve by the group gamma. So there are really 5 classes of curves. And in fact, they're secretly labeled by affine Dynkin diagrams. They're secretly labeled by the affine Dynkin diagrams A0, D4, E6, E7, and E8. And what Chen and Zhang proved, they proved that if you take the moduli space of the character variety for a structure group A of type A, n times the order of the group gamma. So GL n times order of gamma in each of the cases for an arbitrary n. So these are infinite sequence of moduli spaces for which it happens. Then the P equals W conjecture holds for this particular curve and this sequence of groups. And then there is an even more recent, very interesting result due to De Cataldo, Molik, and Shen from last year, who proved that the P equals W conjecture is true for a curve of genus 2 and G of type AN, arbitrary G of type AN for any n. So these are some of the results that we know. And they're proven quite differently with people who have invented actually quite sophisticated methods to prove these results. But there are also some other results which are very interesting and illuminating that do not quite prove the classical P equals W conjecture, but very close variants of that conjecture. So I'm going to mention 3 of those. So first, there is a result of Zhili Zhang from, again, a couple of years ago, who proved that the P equals W conjecture holds for 2-dimensional cluster varieties. So he showed that if you have a cluster surface, you can construct from the type, it's just the type of the cluster surface, there are 2 types of them labeled by an integer, determines an elliptic surface, which is a local elliptic surface. It's a surface, it's an elliptic vibration over a disk, which depending on the cluster variety can have either 1 singular fiber or 2 singular fibers, and the singular fibers are of type I, Kodaira type I. So they're wheels of rational curves. So Zhang proved that for any cluster surface, you can construct such an elliptic surface with the property that the cluster surface and the elliptic surface are diffeomorphic. The elliptic surface is not unique and the diffeomorphism is not canonical. So there is a whole deformation space for those elliptic surfaces, and they're all diffeomorphic and happen to be diffeomorphic to the cluster surface. So there is a kind of a non-canonical diffeomorphism, but in fact, the non-canonical diffeomorphism turns out to be a unique homotopy equivalence. All diffeomorphisms are isotopic to each other. And so it induces a unique isomorphism of cohomology, and Zhang proved the P equals W conjecture, that the weight filtration on the cluster surface matches the perverse Leray filtration on the elliptic surface. And then there is a sequence of very interesting works of Zior-Szabo and Nemeti, where they show that the P equals W conjecture holds for irregular character varieties that correspond to all of the Penlevé equations. So the Penlevé equations of type 1 through 6, they control the isomonodromic deformations of some irregular connections on the projective line. And if you look at the moduli space of those irregular connections, you can ask the P equals W problem from them. And Szabo and Nemeti gave actually two different proofs for the existence of the P equals W isomorphism. And the last variant I wanted to mention is this really beautiful work of Dansko, McBreen, and Schende from last year, where they showed, so it's actually a much stronger and general version of the theorem of Zhang. It's subsumed theorem of Zhang on the cluster surfaces. And it shows that the P equals W conjecture holds for the Hausel-Proudfoot varieties. So if you have any finite graph, I'm calling it T, Hausel and Proudfoot, they assign to that graph two algebraic varieties that they cunningly called B of T and D of T for like Betti version of the variety and the Dolbeau version of the variety. So B of T is affine and D of T is actually an integrable system. So this is some kind of an analog of a multiplicative quiver variety. And they conjectured, at least for the graphs of genus 0, that that these two varieties are actually diffeomorphic. And what Dansko, McBreen, and Schende proved, that they proved that they are indeed diffeomorphic. And again, there is a whole sequence, there is a whole family of diffeomorphisms, but they're all isotopic to each other. Induce a canonical isomorphism of cohomology, and that isomorphism identifies the perverse Leray filtration on the D of T variety and the weight filtration on the B of T variety. So these are versions of the generalizations of the classical P equals W conjecture that are very close to it and have been proven. And again, they're proven in different ways, and they're interesting methods that people have developed in order to prove them.
Tony, I think there was also last year a paper by Felicetti and Mauri about
yes.
P equal W for character varieties with symplectic resolutions.
Yes, for elliptic curves.
It's really interesting because it may be related to Coulomb branches for 3D n equal 4. Some relation.
Well, all of these are related actually to Coulomb and Higgs branches. I mean, all of these variants.
No. But 3D n equal 4, not 4D n equal 2, like conventional.
Yeah, I mean, I'm sure that I'm missing many other that I mean, there is also a numerical approach to the P equals W conjecture by Hausel, Zenesh, and I forgot who else. So there are many other results that I'm not mentioning, but yeah. So anyway, I just want to advertise this subject. I mean, it's very interesting and should have deep relations to mirror symmetry that haven't been explored yet. So I think this is my, let me see, almost the end of what I want to say about the classical P equals W conjecture. So there is one more bit I want to say, which is actually a very useful and powerful theorem of de Cataldo and Migliorini that gives a description of the perverse Leray filtration on an algebraic variety in terms of hyperplane sections. And this is actually what you use in practice. So I just want to explain it because it will become relevant for the later discussion in mirror symmetry. So here is the version, the simplest version. I mean, they have a more general statement. This is the most basic statement, but that's the one we'll be using. So let me state it. So if you have a smooth affine variety B of dimension n, you can embed it in an affine space and then choose a generic linear flag in the affine space. Just choose a generic full flag of linear subspaces in that affine space. And look at the hyperplane sections of your affine variety. So you get the flag of affine subvarieties going from codimension 0 to codimension n, which are just generic linear sections. And then the theorem of the Cataldo-Migliorini says that the perverse Leray filtration for any complex of constructible sheaves on B, it's really given by the geometric filtration given by the Flock. So it says that if F is any constructible complex of Q vector spaces, and if you look at the cohomology of B with coefficient in the perverse truncation of F at degree minus K, this is the same as the kernel of the map from the cohomology of B on F to the cohomology of F on the K plus I minus 1 step of the Flock of subvarieties for any generic Flock. So this description is very hands-on. You don't need to compute supports of cohomology. And so it's very useful, and that's what we are going to be using. So that's the end of my introduction to the classical P equals W conjecture. So I'm going to move now to the mirror P equals W conjecture. So if there are any questions on the classical story, now is the time to ask them.
So is it restricted to kind of varieties, or there is a version for stacks?
Well, there are various versions. Certainly, there are expectations for the P equals W conjecture to work for situations where the varieties are not smooth but are orbifold, so they have a Deligne-Manfred-Stack resolutions. The statement really works for the Deligne-Manfred-Stack resolutions, or in fact for Crepant resolutions if they exist. Also, there are versions of the. I think Maury had a sequence of examples and statements that he proved for the P equals W conjecture on singular spaces by using intersection cohomology rather than cohomology.
But it's no more than Deligne-Mumford stacks, no Artin stack, because Higgs they kind of it's not a Deligne-Mumford stack, yeah.
Yeah. So if you put more complicated structures in order to resolve the singularities, like if you have Artin stacky points or derived structures, and you ask, do you need to modify the statement of the conjecture for it to make sense? It's much more complicated, but both the Hodge theory and the perverse truncation need to be modified in those cases. So because the Hodge theory doesn't make sense on the nose for Artin stack, so you need to do something.
Nobody tried, yeah.
I don't know of any statements that people have tried to make precise, but probably you can make something. I mean, we still don't have a good grasp of why the conjecture is true, right? So I think until we have a conceptual understanding of why it's true, it's going to be hard to make a precise statement when you need to modify the conjecture.
Okay.
All right, so let me move on and talk about the mirror P equals W conjecture.
Sorry, I think Sasha Kuznetsov wants to ask something. Sasha.
Yeah.
Tony, I'm sorry. So you explained that there are several versions of varieties for which similar conjectures apply, right?
Mm-hmm.
Do all of them have this property that W2K equals W2K plus 1?
All the examples that I've mentioned so far have this property, yeah. But once we move to the mirror one, that's not going to be the case.
Okay. Thank you.
Yeah. But all the examples I've mentioned so far have this property. Okay, so the mirror P equals W conjecture, it really starts with a very interesting and exciting observation by Ludmil, who noticed that if you take the P equals W for a character variety and the mirror symmetry for the same character variety, you can try and combine them and get a meaningful statement. So once you combine them, you get some version of the P equals W matching for a general pair of mirror local Abel varieties. And then you can test that statement and actually prove interesting theorems. So that's what I'm going to try and explain now. So let me try to go through through that observation of fluid mills. So if you have this Pico's W conjecture for the character variety for a group G and the Dolbeau space for the group G, you can try to combine it with mirror symmetry, say with homological mirror symmetry. And you expect that the character variety for the group G is homologically mirrored to the Dolbeau space for the Langlands dual group. And in fact, this is based on the fact that the Dolbeau space for the group G and the Dolbeau space for the Langlands dual group are T-dual. There is a Fourier-Mukai duality on the torus fibers for the affinization maps, for the Hitchin maps. And we know that this is the case away from the discriminant. And in fact, we know it's the case in codimension 1 in the discriminant, and it's most probably the case everywhere. So that's what justifies this expectation that the homological mirror of the character variety for G is the Dolbeau space for the Langlands dual group.
So what are the symplectic structures? I know mirror symmetry in C infinity case. And so what is it?
You mean in the first statement, in the homological mirror symmetry?
Yeah, because
right. So I mean, depends which all of those guys are hyperkähler, right? So so depends
that's
which.
my question. What do you mean by homological mirror symmetry?
So in this setting, what I mean is that you're taking the B side to be on the character variety side. Okay. So that complex structure is canonical. It's
But what is this real symplectic structure you choose?
The real symplectic structure is the real part of the homomorphic symplectic form on the Dolbeau space.
So then it looks like it's mirror duality between M Betty and M Betty. No. With rotated complex structure.
No, it's not M Betty and M Betty. It's M Betty and M Dolbeau.
I don't think so. But go ahead.
I don't understand what you mean.
No, I mean that it's rather look as two M Bettys if you take the real part of the complex.
I just don't understand what that statement means, because M Betty and M Dolbeau are diffeomorphic. So as symplectic manifolds, they're the same.
As well, first the C infinity manifold.
Yeah, and then you're taking a symplectic structure, which is a C infinity symplectic.
So you mean that you take the real part of the holomorphic form on M Dolbeau and use it as a C infinity symplectic form on M.
That's how mirror symmetry works, right?
Well, there are different.
But if you try to reverse the A to B, then the B structure on M Dolbeau will be the complex structure.
For example, the same Hausel, like long ago, I believe, like maybe 20 years ago, he formulated this mirror symmetry jointly with Tadeus as mirror duality between M Dolbeau and Dolbeau.
Because it was only homological. I mean, I'm talking about that, so why don't you listen?
All right, yeah, so I don't interrupt. Okay.
I mean, it's on the slide that's on the screen right now.
Okay, thank you. Go ahead.
Okay, so yeah, so what I'm saying is that there is actually an algebraic duality, a Fourier-Mukai duality between M Dolbeau and M Dolbeau for the Langlands dual groups. And then, the mirror symmetries, you take this one and you compose it with some kind of a hyperkähler rotation on one side, which rotates you from M Dolbeau to M Betty. And so the fact that there is this Fourier transform that's inserted in mirror symmetry, it suggests that if you take the direct image of the structure sheaf with respect to the Hitchin vibrations on the site of G and on the site of the Langlands dual of G, you'll get some constructible complexes which are morally Verdier dual. So this you need to prove, of course. It's all intuition here. It's a heuristics. So on the non-elliptic locus you can prove it, but you really want to say it in some precise way everywhere. But if that works, then you expect that the weight filtration on the M Betty space is going to be then exchanged for the group G, is going to be then exchanged to the perverse Larrey filtration on the mirror guy, which is the M-Dolbeau space for the Langlands duo group. But you know, because there is some kind of Verdier duality or modified Verdier duality inserted in the process coming from this Fourier transform, the perverse Larrey filtration will have to be relabeled. So the idea is that the perverse Larrey filtration is something happening on the base, and it interacts well with the perverse T structure. So it's just gonna relabel the perverse Larrey filtration on one push forward and the perverse Larrey filtration. It's gonna exchange the perverse Larrey filtration on one push forward with the relabeled perverse Larrey filtration on the other push forward. And because of that, you expect some kind of a P equals W statement, which I'm gonna call now the mirror P equals W statement, which says that the weight filtration on the character variety for G is going to be related to appropriately labeled perverse Larrey filtration on the character variety for the Langlands duo guy. So this motivates this P equals W conjecture, mirror P equals W conjecture. So I'm going to state that now precisely. So if you have a smooth projective variety of dimension D, and you have a strict normal crossing divisor, which is anti-canonical, you can look at the complement of that strict normal crossing divisor and look at the cohomology of that non-compact Calabi-Yau variety, and it has canonical Hodge and weight filtrations. And we can look at the Hochschild homology of that non-compact Calabi-Yau, and I'm gonna write it as the direct sum of the PQ pieces with respect to the Hodge filtration for Q minus P equals I. So that's going to be the Hochschild homology of degree D plus I. So it's the Pth step graded piece of with respect to the Hodge filtration of HP plus Q of U, which is really the Qt cohomology of X with coefficients in the logarithmic forms of degree P. And then the weight filtration on the cohomology of U induces a weight filtration on this cohomology with coefficients in the logarithmic forms. And you can describe that explicitly. You have the codimension I residue map. So I'm suppressing the orientation local systems here because they don't do anything, just clutter the notation. So if you take the logarithmic forms with coefficients in logarithmic forms on the divisor of degree P, there is a residue map that maps you to the logarithmic forms of degree P minus I on the points in the divisor of multiplicity I. So take the codimension I intersections of all components of the divisor, normalize that space to get something smooth. So that's what's called Y nu sub I. And then in that smooth space of codimension I in the divisor, there is a divisor, which is the intersection with the other components, which is again normal crossing. And you take forms of degree P minus I with the logarithmic poles on that divisor. And the residue map just restricts a form of degree P with logarithmic poles on Y to a form of degree P minus I on this codimension I guy on the induced divisor with logarithmic poles on the induced divisor. And then the ith step of the weight filtration is just the kernel of that map. This is the ith step on the weight filtration on the bundle of forms, and you can define the ith step of the weight filtration on the cohomology by the image of the I minus P plus Q step of the cohomology of the I minus P plus Q step on the sheet. So that's the Lee's definition of the weight filtration, explicitly on these Hodge pieces. And for the purposes of the P equals W mirror conjecture, we need to relabel that slightly. So I'm going to call this WJ twiddle, and it's just going to be the image of the Q cohomology of the WJ piece of the weight filtration to the Q cohomology. So there is this delink shift is not there. And then you can define the WJ twiddle filtration on the D plus I Hochschild homology, which is just going to be the sum of those pieces on all the Hochschild pieces, on all the Hodge pieces. And if you take the mirror of the non-compact Calabi-Yau variety U, so in the sense that I also was talking, say, in the last lecture, mirror symmetry in the complement of an anti-canonical divisor, then this has a natural affinization map, so I'm going to call this affinization map the hybrid Landau-Ginzburg model that's mirrored to the pair XY. The motivation for the terminology is that that's what the physicists called it. And so if Y has n components, then if you trace through Denis' construction of the mirror of the complement of the anti-canonical divisor, then the mirror is just a pair of this Y check guy, which is the SYZ U check guy, which is the SYZ mirror of U, and a homomorphic function, which counts pseudo-homomorphic disks in X with boundaries on the fibers of a SYZ vibration in U, and have order of contact 1 with Y. So by construction, the function actually splits into a sum of functions, H1 through Hn, where Hk counts disks that have order of contact 1 with the kth component of Y. And so you get this hybrid Landau-Ginzburg model, which is really a map from U check to the n-dimensional affine space, given by all those pieces determined by the components. And in the cases where you can actually compute the mirror, it really factors through the affinization. So that's why it's reasonable to call this affinization map the hybrid Landau-Ginzburg model, which is mirrored to the pair, to the Fano pair. Now you choose a generic FLAC in that target affine space of linear subspaces and define the perverse Leré filtration to be the kernel of the map, the restriction to the preimage of the hyperplane sections with the FLAC, with the shift, which is J minus K plus 1. And so here is the mirror P equals W conjecture. It says that under homological mirror symmetry, the identification of the kth Hochschild homology of U with the kth cohomology of U check should match the weight filtration defined with the labeling I had before, W twiddle J, with the jth step of the perverse Leré filtration with the labeling we have here. And so to go back to Sasha's question, this is a setting where the steps of the weight filtration don't collapse between even and odd. And so there are quite a few results already in this direction, verifying this conjecture in many examples. So there is the results by Andrew, by Ludmil, by Vitya Przylkowski, and quite a few others. And Andrew is going to actually review some of those in his talk. There is also a refined version of the conjecture, which takes into account Hodge filtrations, which is the one that we are trying to prove in our project. It's quite interesting, and I just want to mention it, but Andrew is going to talk about it in more detail. So what is it about? It's a refinement of the mirror P equals W conjecture, which matches weight filtrations and perverse Leré filtrations. And you want to refine to basically split get a statement that refines the statement that you want on the splitting with respect to the Hodge filtration. It's quite difficult to trace what happens with the Hodge filtration through the mirror duality, but there is a very good substitute actually, which we know from topological SY mirror symmetry for compact coabials for quite some time now, due to the analysis that Mark Gross did about topological SYZ fibrations. You can substitute information about in the SYZ mirror symmetry picture, you can substitute information about the Hodge filtration with information, topological information, which is information about the Leray filtration with respect to the SYZ fibration. So here is how it looks like. So you take U and you check, which are SYZ dual. They have dual Lagrangian torus fibrations over some base S. There is a discriminant in that locus, in that S space, and the complement of the discriminant I'm denoting by S0, and the fibrations, the smooth torus fibrations over the complement of the discriminant are U0 and U0 check. And if for the sake of discussion and simplicity of the discussion, you assume that pi and pi check are simple, cohomologically simple, which means that the push forward of the constant sheaf with respect to pi or pi check is actually the middle perversity extension from the push forward on the smooth part of the fibration. So it's the J lor star of the push forward from the smooth part of the fibration. And that happens quite a bit in tame SYZ fibration. So if you assume that's the case, then the Leray spectral sequence for pi and pi check, and assume also that the Leray spectral sequence degenerates, which also happens quite often, then you get a decomposition of the cohomology of U with coefficients in Q into Leray pieces for the push forward, and the same for U check. And where the duality exchanges those pieces by switching the degree of the cohomology. And in particular, this tells you that the Q cohomology of the extension from the smooth part of the P push forward is the same as the Q cohomology of the extension from the smooth part of the D minus P Q push forward for the dual fibration. And so this is what Mark Gross did for compact coabials and topological SYZ fibrations in the neighborhood of the large complex structure. These actually guys match the Hodge filtration in that case. Or in fact, it's a filtration that splits the Hodge filtration, but it's good enough to give you information about the Hodge filtration. And so you expect that in this non-compact situation, that's also the case, that this should be HQ omega P with coefficients in log Y, is that HQ of the P cohomology pushed forward for the SYZ fibration. And then you can use this to refine the mirror P equals W conjecture. And so you can actually define weight filtrations and perverse Leray filtrations on those pieces for the dual SYZ fibrations. And you can conjecture that they actually match. So Andrew is going to explain the definition and how we are planning to approach the conjecture and how we can get examples actually where we can prove that. But I just wanted to mention that this refinement is there. It actually exists. The price you pay is you replace the Hodge filtration. You don't refine with the Hodge filtration on the nose. You refine by some topological filtration that depends on the SYZ fibration, which in principle should give you the same information as a split filtration that's opposite to the Hodge filtration. Okay, so that's the end of the general discussion of the mirror P equals W conjecture. And as I said, I didn't do any examples and didn't state any results, but Andrew is going to do that. Now, in the remaining 10 minutes, I want to talk about Sukjoo Lee's work and show you how formal structure of homological mirror symmetry allows you actually to prove the Pico's W conjecture by combinatorial considerations, or reduce the mirror Pico's W conjecture to a version of the Pico's W conjecture that's easy to prove directly by using mirror symmetry.
Tony, may I ask?
Yeah.
For conventional P equal W, like Hausel and others, do you have this U and U do? I mean, mirror dual SYZ fibrations? I do not see them.
No, I mean, this mirror duality, this changes the spaces, right? U and U check are not diffeomorphic anymore.
Yes, but what they are, you should have two mirror dual. I mean, just the setup.
No, the setup is, I tried to explain that when I was doing the motivation, that the mirror P equals W conjecture is really a composition of for the Betty.
I see.
Betty modular space. It's really a composition of the usual P equals W conjecture with the Fourier transform.
Okay.
And the Fourier, the effect of the Fourier transform is that it just transforms the perverse Leray filtration to the perverse Leray filtration for the dual space, but maybe relabeled.
All right. So it's just reformulation. I mean, just sort of composition of two
dualities.
Okay.
But at the end, the statement looks the same because the Fourier transform doesn't do anything to the it just sends a perverse to perverse filtration. That's all.
All right. So may I say that this SYZ mirror dual for conventional P equal W, it's still two M del Bos for G and G Langlands dual with the real.
No, that's the mirror dual. That's the Fourier transform you're taking. Yes.
All right. Thank you.
All right. So let me say a few words about Sukjoo's work. So we are again in that setting that we were discussing, which is homological mirror symmetry in the complement of an anti-canonical divisor. So the basic case, which is one of the results that Andrew is going to talk about, is you start with a smooth Fano X and a smooth anti-canonical divisor D. Then the mirror of that looks like a Landau-Ginzburg model. So you have a smooth variety Y of the same dimension as X. You have a potential. So sorry, I'm changing slightly the notation. Before Y was my divisor. Now D is my divisor. Y is the mirror. So the notation is local to this story. So you have a variety Y, a potential W, and you are marking one smooth fiber of that potential. And there is this relative mirror symmetry statement that I also actually talked about on surfaces in the previous talk, which says, so it's B to A. So the B side is on the Fano side and the A side is on the Landau-Ginzburg side. It says that the derived category of coherent shifts on X or the derived category of coherent shifts on the Calabi-Yau hypersurface, they get exchanged with the Fukaya-Seidel category of the Landau-Ginzburg model or the Fukaya category of the smooth fiber. And that induces actually isomorphisms of cohomologies. So the cohomology of X and the cohomology of D get matched with the cohomology of the pair Y smooth and the cohomology of the smooth fiber. And the same happens with the Hodge number mirror flip. So the PQ piece of X gets mapped to the D minus PQ piece of the pair. And the PQ piece of D gets mapped to the D minus 1 minus PQ piece of the smooth fiber. So that's just a very quick review of what we expect in Fano mirror symmetry for a smooth anticanonical divisor, relative Fano mirror symmetry for a smooth anticanonical divisor. And in fact, it's more complicated than that, right? You have this whole diagram of categories. So you have a localization triangle that goes from derived category of coherent shifts of D to the derived category of coherent shifts of X to the derived category of coherent shifts on the complement. And there is an analogous triangle for the Fukaya type category. So the Fukaya category of the fiber goes to the Fukaya-Saido category of the potential and goes to the Rapp Fukaya category of the total space. And you know, all the functors here are actually defined independently by either restricting Timbals or doing Hamiltonian flow around infinity, which is this Orlov functor of a Buzet Ganatra. And the horizontal sequences are localizations. So this whole thing is supposed to commute with homological mirror symmetry being giving you the isomorphisms vertically. And if you pass to Hochschild homology, then you get isomorphisms between Hodge sums of Hodge pieces on the Calabi-Yau hypersurface or on the Fano, with the cohomology of the fiber of the Landau-Ginzburg model or cohomology of the vanishing cycles, the cohomology of the pair. And then the point is that these identifications, if you look at them carefully for a smooth divisor or for a map to a one-dimensional affine space, so proper Landau-Ginzburg model, these are just U1's pages in the respective spectral sequences that appear in the P equals W conjecture. So the top one is the U1 page in the weight spectral sequence for U, and the bottom is the U1 page of the spectral sequence for the filtration by subvarieties, the hyperplane sections for Y. So this actually allows you to prove, once you know homological mirror symmetry for this mirror pair, allows you to prove the mirror P equals W statement. So there is this result, which Andrew is going to talk about more, I guess, due to Harder, Katzarkov, and Przyokovsky, which says that under these assumptions, homological mirror symmetry gives you actually an isomorphism of the graded pieces with respect to the Hodge and the weight filtration added up in the Hochschild way, with the graded piece of the perverse refiltration. And in fact, you can refine that by using monodromy weight filtrations with respect to the action of the Serre functors on both sides and get it on the pieces. So, so as a corollary from that, you get that if you know homological mirror symmetry for a Fano with a smooth anti-canonical divisor, and the mirror Landau-Ginzburg model happens to be a complex manifold that has a Tate mixed Hodge structure, then the mirror P equals W conjecture holds in this case. And I'm almost out of time, so I'm sorry. I was gonna explain that Sukjoo actually could use this statement and the combinatorics of gluing of Landau-Ginzburg models into hybrid Landau-Ginzburg models to prove the statement for a normal crossing but not smooth anti-canonical divisor. So I have the statements here, and you can look at them on the slides, but I don't want to run over time. So the punchline is that Sukjoo in his thesis, as part of his thesis, could actually show that the statement of Harder, Katzarkov, and Przyokovsky plus some gluing procedure for ordinary Landau-Ginzburg models for the components of the anti-canonical divisor that gives you the hybrid Landau-Ginzburg model, gives you a proof of the mirror P equals W conjecture in the case of non-smooth but normal crossings anti-canonical divisor. And also the same procedure actually gives him a way to proof. This is all related to this Hodge theory of Landau-Ginzburg models that Maxime, Ludmil, and I worked out a few years ago in order to prove the Bogomolov-Tian-Todorov theorem for Landau-Ginzburg models. And so Sukjoo actually could bootstrap that again by the same gluing procedure to prove both the Hodge theory degeneration and Bogomolov-Tian-Todorov theorem for hybrid Landau-Ginzburg models in the same way we did it for ordinary Landau-Ginzburg models. So I'm going to stop here and wait for questions.
All right, let's thank Tony. Questions?
So, Tony, somehow you still don't have a better understanding of this P filtration.
No, I mean, there isn't, I mean, there is, no, we have a better understanding of why the P filtration will match the weight filtration in this mirror setting. And Andrew is going to mention that when he defines the P filtration, and so you, in the SYZ refinement, you'll see. So the P filtration, of course, it's coming from this. You use the hyperplane section description by this flux, and you can understand that as extracting the weight filtration on the other side of the mirror through the flux by doing tropicalization. So Andrew will mention a little bit about that. So you get some glimpse of why this flux support filtration should be mirrored to the weight filtration, but there is no theorem yet. There is no conceptual explanation of, oh yeah, that's it. Plus, I want to say that in the ordinary Pico's W conjecture, you still need to do a Fourier transform. You need to relabel that just by using the Verdier duality on your space. And since this basis of the SYZ fibrations, so this is all happening on the basis of the SYZ vibration, and typically the basis of the SYZ vibration are actually stratified. So the Verdier duality, is interesting. So when you try to see what happens, you need to do the analysis much more carefully than anything I've said already.
So for original P equal W, this tropicalization, is it related to Carlos Simpson ideas about this, the base of Hitchin system and compactification of M-Betty by means of the skeleton?
Most probably yes, but these varieties are way too complicated to actually test that directly. Maybe you can test it for two-dimensional character varieties, and see that it is indeed this geometric Pico's W conjecture of Carlos, but we haven't. I mean, we're still trying to get the general statement as cleanly as possible in cases where we can actually talk about mirror symmetry on a firm ground.
Okay, thank you.
Other questions? If not, let's thank Tony again. And we proceed at 1 p.m. Eastern Standard Time with the talk by Yuri Chinkel. Thank you.